Thanks, Peter. So I'm going to give a project status, and as I have the ambition to show the deployment video, which is 12 minutes, I'm going to try to go fast, otherwise Peter will kick me out of the podium. So JWST, the first thing I always start with this slide. I think some of you have already seen it, but it's a big project. What I'm showing is just not my work, it's the work of a lot of people. And I've also been stealing from many presentations to prepare this one. Here, what I'm going to address today is a few words about the JWST mission, an overview, its status, and in particular what is left to do between now and launch, because I will start to show you nice things. And you could just ask, but you're already almost there. Why almost 2 years till launch? So you will see that we still have some work to do. And then a brief overview of the JWST capabilities. It's really an overview because tomorrow you have all the talks with, which will go in details through the various modes. So JWST, and I think probably if you're here, I don't need to convince you, but will be one of the great observatories of the next decade.
We need to stop you to reconnect to web.
Yes, just go ahead. Okay, and sorry. So great observatory of the next decade, and it's a joint mission, so it's a NASA-led mission, but with contribution from the European Space Agency and the Canadian Space Agency. And the setup in terms for the astronomers is similar to the HST ones, and in return for contribution of ESA to this mission, the astronomers and scientists of the member states will get a minimum of 15% of the observing time of JWST. To be launched at the end of 2018, October, and the official minimum mission duration, the thing you put in the requirement, is 5 years, but every consumable in the observatory is actually scaled for 10 years of science. So it means 10.5 years because after you need to commission before that. Thanks. So who does what in some way, and that's it's almost an unbiased slide because I've chosen the most visible color for ESA. But so it's a NASA-led mission. There is a lot of white, the spacecraft, telescope, instrument NIRCam, the Science and Operations Center, STSCI, and a lot of also communication. But ESA is actually providing ESA in Europe are providing quite important elements of this mission. One is the launcher. JWST will be launched by an Ariane 5 rocket. We're also providing one full instrument, near spec, and also there's a 50% preparation for the mid-infrared instrument MIRI. And basically Europe is providing the instrument, and the US are providing the cryogenic cooler and also the detectors. Thanks, Bruno. And something which is not negligible, ESA is providing also staff member, is providing personnel that will support the operation. And then in blue, you have the Canadian Space Agency is providing the guider and one instrument called NIRIS. In terms of science, and the same thing, I'm not going. I'm sorry. Cannot change slide. Oh, like that I can. So with the mouse I can. So in terms of science, it's a general observatory. So you're going to get a very broad set of topics. And when the mission was designed, it basically the 4 topics that were put in ahead were one very close to cosmology, which was the first light, the end of reionization. Then all the story about the assembly of galaxies, their formation, their evolution, and from really the first galaxies to basically also the peak of their formation, and then beyond. In the story of the origin, also birth of stars and protoplanetary systems, and then planetary systems, including our solar system, and including a topic which, since JWST was designed, has actually become a really big and hot topic, exoplanets. There is a review going through these different fields from Gardner et al. In 2006. But at the end of the day, it's an observatory. You will make proposals. There will be a time allocation committee. So exactly what JWST will do is going to be up to you. The hardware. So that's we get questions from time to time about Star Wars shape of this observatory, but it was not done to look like one of the starships of Star Wars. But in fact, what you have is it's a big telescope, 6.5 meter diameter primary, segmented. You can see the secondary here. And you want to keep it in the shade because it's a passively cooled telescope. You want to keep it permanently in the shade so it can go down to 40K. And for that, the shape of a sun shield that you need to put it in the shade is this type of size. It doesn't look that big, but if you think about it, 6.5 meter diameter telescope, the sun shield has the size of a tennis court. Okay, so this is going to be the side which is be always in the shadow. The other side of the observatory is going to be always facing the sun, and that's where you get the communication antenna, you get the solar panels, and the instrument, the payload, they are actually sitting on the back of the telescope here. Yep. So it's not only a CAD drawing, it's becoming reality, and you have already seen in Marco's slides. And this one, I think we're going to show it for quite a while. This year, basically, the telescope itself was integrated, and it's quite impressive. It's in a large clean room at the Goddard Space Flight Center. So you see the segments, the secondary, and the tertiary, and the what we call fast steering mirror on there. And this is John Matter. This is the overall project scientist of mission. He's actually taking a selfie in front of primary. I missed this one. I didn't manage to be there when we could see it this way. 4 instruments covering, in fact, from the near-infrared to the mid-infrared. And in fact, you have 3 near-infrared instruments and 1 multi-purpose mid-infrared instrument, MIRI. MIRI is the mid-infrared instrument. That's the one which has been built in partnership between a consortium of institutes in Europe, ESA and NASA. The PIs in Europe, Gian Wright, and in US, George Rickey. Then you have a suite of near-infrared instruments, NIRSPEC, the near-infrared spectrograph provided by the European Space Agency. Then you have NIRIS, near-infrared imager and slitless spectrograph. And on the same structure, you have the fine guidance sensor, which is really in charge of the fine guidance, the fine pointing of JWST, with the PIs René Doyon and Chris Willott. And then we have NIRCam, the near-infrared camera, developed under the responsibility of University of Arizona, and the PI is Marcia Rickey. So this is the suite of instruments, and you will see at the end of my presentation, it provides you quite a lot of modes and a very versatile set of instruments. Sorry, I keep pressing on the wrong button. What you have I've shown just before, it's the telescope, and these are the instruments. And also this year, there was the installation of the instrument on the back of the telescope. You can see the telescope is face down, and they are on the crane. It's quite a frightening image. Everything went well, but yeah. So sometimes you will hear about OTIS. This is the combination of the instruments and the telescope. Sun shield, here also, it's not only CAD drawings. The sun shield, I will show you the deployment after, but it's actually protected when it's folded. And these structures are the rigid structures that will protect the sun shield during launch. This is I like this image with a person in the middle of the sun shield here. And this is actually a flight membrane, so one of the real ones. And remember, size of a tennis court. And this part, very complex, is in fact the center. And that's really where you connect the warm part of the observatory to the cold part. So it's actually very complex, and a lot of attention is paid there, so you don't get heat flowing from the warm part to the cold part. Something we usually forget because it's not that spectacular, it's the spacecraft itself, so on the other side of the sun shield. But here also, it's progressing and it's being assembled. And I think here it's the star trackers there. Solar panels. everything you find on a spacecraft. So 6.5 meter diameter primary sun shield the size of a tennis court, and this does not fit in any fairing of rockets. So the solution was to fold it and then unfold it once in space. So I'm going to show you the deployment after, but these are the sequences, and you will see all the elements almost of JWST are actually can be folded and folded. So 12 minutes here, and I hope it works. Starts with a launch. You don't hear the noise, but it's close to the jungle, so it should be with.
As the sun rises over the Guiana Space Center, the team conducts final checks on the health and status of the Ariane 5 rocket and its payload. The James Webb Space Telescope, NASA's #1 science priority. The Webb telescope is designed to look back to a time when stars and galaxies were first forming, over 13.5 billion years ago. With its revolutionary design and capabilities, the Webb telescope is about to unleash a new dawn of discovery.
À tous de vidéo, attention pour le décompte final. 10, 9,
Done in French.
Seconds before liftoff, the Ariane 5's liquid-fueled engine comes to full power, followed by the ignition of the 2 solid rockets. We have liftoff. The Webb telescope is finally on its way, the result of years of study and development by thousands of team members in the United States, Canada, and Europe. Webb spacecraft ascends nearly vertically through the heavy lower atmosphere of Earth. As the rocket reaches maximum acceleration, the spent solid rocket motors are jettisoned safely into the Atlantic Ocean. Reaching the upper atmosphere where protection is no longer needed, the payload fairing is jettisoned and falls away.
So you see folded, what it looks like.
Accelerating through the atmosphere, the Ariane 5 rocket's first stage expends its fuel and shuts down. The empty first stage then separates from the upper stage. After first stage separation and before second stage ignition, the Webb telescope has a slightly downward trajectory as it speeds over the Atlantic Ocean. The upper stage motor ignites and the ascent to L2 resumes, never again to be interrupted. The exposed telescope is delicate and must be protected from the sun's fierce heat. To avoid overheating and damage, a carefully designed series of oscillations are performed that provide the necessary protection. Near the end of powered flight, the roll program stops and the launcher then assumes the proper attitude for separation.
So here, basically, you're only James Webb Space Telescope.
After separation from the Ariane upper stage, the Webb telescope continues its journey to L2 under its own power, taking the next step to its final orbital station 1 million miles from Earth. The Webb telescope is about to unleash a new dawn of discovery.
But this stage also, the only thing which has been deployed is basically the solar panels, because the first thing you need is power. Okay, so that's then we start something.
The Webb telescope separates from the launcher's second stage. The white ring close to the Earth represents the Hubble Space Telescope's orbit, and the larger orbit is the geosynchronous orbit where most telecommunications satellites are located. The solar array is Webb's first deployment. When completed, all of Webb's electrical power needs are satisfied by the solar array for the remainder of the mission. The onboard control system continually monitors and updates the attitude to ensure power generation and thermal safety. To preserve the cleanliness of the mirrors, thrusters are located only on the sunlit side of the observatory. The trajectory is designed without employing a retrofire, which necessitates pointing the delicate telescope at the sun. If course corrections are needed, these velocity additions must be done early in the flight to most efficiently use the mission's limited precious fuel. After completing mid-course corrections, the Webb telescope passes the orbit of the Moon.
So this was the antenna, one of the communication antenna. It was deployed. And you see already second day. This is going to be a
Webb's initial transformation is the deployment of the sun shield pallets.
These are the structure I showed in my slide. Second one.
The tower separating the telescope and instruments from the spacecraft and sun shield is next.
It's really raising completely the telescope away from the sun shield.
Next, the aft flap deploys. This is key to managing momentum buildup and fuel consumption. This structure helps to balance the pressure from the sun's light on the Webb telescope around its center of mass. After the sun shield pallets reach their final positions, the membrane launch restraints are released. These have kept the sun shield membrane safely in place from final stowage at the Northrop Grumman facility in California through shipment and launch. The sun shield protective covers roll back, permitting membrane deployment. The covers over the core region release next.
So the core region is this center region connecting.
Then the
core
mid-booms
to the core.
extend and the sun shield assumes its hexagonal tennis court-sized shape.
Deployment of a sun shield. So 50.
It is now time to tension the sun shield membranes, each thinner than a human hair, pulling each of the uniquely sized and shaped layers to their optimal position. When deployed, the sun shield allows the telescope to cool to 385 degrees Fahrenheit below zero, cold enough to liquefy air, while the layer closest to the sun is almost 190 degrees Fahrenheit above zero, nearly the boiling point of water. It's of almost 600 degrees. Truly fire and ice. Once in the shadow of the deployed sun shield, the telescope and instruments continue cooling down to their final operational cryogenic temperatures. At the completion of membrane tensioning, the secondary mirror deploys into position and is latched rigidly in place. The aft deployable radiator releases and springs into position, allowing the instruments to radiate their waste heat directly into space and away from the telescope. Disposing of excess heat is crucial to the mission so that it does not overwhelm the faint infrared signals to be collected from the cosmos. The cord fold wings deploy and latch in place, completing the major deployments of the largest telescope in space.
And that's basically the last step. Then we continue to I'm a little bit short on time, so I will get it here.
As the
But that's the principle, and this is going to last roughly 3 weeks, and it takes approximately 1 month to reach the L2. But once you are there, you don't stay stick at the middle of L2. You will make a big orbit around L2. And I think in terms of status, the big thing, and I'm happy that I'm showing this slide for more than several years now, basically we are on track, and the launch in October 2018, we still have more than 6 months of contingency in the schedule, and doesn't mean that anything is rosy and no problem. It means that we have the resources to tackle the problems when they arrive. So next, because you've seen a lot of hardware, now basically we are integrating and testing. So what happens is that the telescope, the Otis, is now being the integration is finalized. It's going to be tested, and then in next year there will be cryogenic testing of this thing, and that will be quite impressive because it's a big telescope, and this is just the door of the cryogenics chamber at the Johnson Space Center. So that's quite big scales. And in fact, it's such a complex test that in order to make sure everything will work, NASA has been actually testing the chamber, the equipment, the procedures on a pathfinder that looks like really very close to the flight hardware. So that's quite a lot. And in parallel, all the work on the spacecraft, on the sun shield is happening, and in particular at Northrop Grumman. And then everything will come together, and then yes, we will launch in October 2018. And so that's the first part, status and hardware. And just very quickly, an overview on the capabilities. JWST is covering from 0.6 micron to almost 30 micron. So you've seen MIRI, the mid-infrared instrument, NIRSPEC, NIRIS, NIRCam, doing the near-infrared, and doing spectroscopy and imaging and coronagraphy. The layout of the field of view, the instruments are not looking at the same place of the sky at the same time. So they have all a dedicated field of view in JWST field of view. You have NIRIS, you have the two guiders, you have NIRCam, NIRSPEC with its spectra, and you have MIRI. So you cannot point simultaneously all different instruments to the same place. Okay, there will be the possibility, there's a talk on parallels, there will be some information on parallels, but in this case you observe two different places on the sky. In terms of imaging, near-infrared, you get NIRCam as the workhorse with two channels that can observe in parallel the same place of the sky, these ones. So you can get the blue, between quotes, and red part of NIRCam observing the same part of the sky with a fields of view of 2.2 arc-minute by 4x4, different samplings. NIRIS has also imaging capabilities in the near-infrared, 2.2 by 2.2 arc-minutes, and MIRI then complement for the mid-infrared. I think the take-home message for JWST in general, not only for imaging, is that there's really a huge improvement in sensitivity with respect to existing facilities, and this will be an extremely powerful observatory with a lot of discovery space. These are the field of view, NIRIS. And NIRCam, what happens is that these two fields, the blue side and the red side, are actually the same one. So you observe at the same time in the up to 2.5 micron and beyond, between 2.5 and 5. And this is the MIRI imaging field of view. Like any imager, they have a battery of, they have a battery of narrow band filters and everything. In terms of spectroscopy, and I think that's take-home message here is that spectroscopy on JWST comes with many flavors. So you will have to look carefully and pick what you need for your science. And you get slitless spectroscopy in the near-infrared, so with NIRIS and NIRCam. You will get multi-object spectroscopy with NIRSPEC. You will get IFU spectroscopy, NIRSPEC and MIRI. You get classical slit and also some modes which are dedicated to time series observation, one of them typically exoplanets. And then you get also aperture for single objects. So you will have a lot of modes. You will have various type of spectral resolutions as a function of wavelength, and you get very low spectral resolution, what we call medium and high, even if for high is not for some, for ground-based in particular, high at 3000 is not very high. But these are the type of range in wavelength and range in spectral resolution that will be provided. You have also coronagraphy, and you will later during this workshop you will get more details on that. And you get basically the different type of coronagraphs, but in the near-infrared through NIRCam, NIRIS, Then you get MIRI with a set covering up to the mid-infrared. I'm almost done. Just you will have a presentation by Jason Carrerai on Wednesday, but you have to know, and this is for reference. Basically, there are places where you can find information on the newsletters, science flyers, white papers on the STSCI website. There is also a description of science teams, and I think white papers. There are some recent ones, exoplanets, solar system, and a large variety of flyers. That's why you will find updates on the flyer which are distributed today and this type of things. And you have articles from newsletter. There will be also, I think Jason Carrerai will talk about that. There is things about tools that will be needed to prepare to do that. And I think, Jeff, maybe you will. So this is, you can find that on the STSCI website. And there's a newsletter, the web update, and that you're able to register on the NASA JWST website, I think. Oops. I think you will see those quite a few times during the conference, but there are conferences, both conferences, workshops to prepare you for the arrival of JWST. One very close is the second Exploring the Universe with JWST in October in Montreal, in Canada. There is a joint Hubble and James Webb Space Telescope conference in Venice in March next year, and there will be a workshop at the last day of this meeting. There is the ESAC 2017 workshop that will be the following workshop for this one. So I think Marco will give more, I think a longer list, but I think it's good if you hear it quite often. There are many things many opportunities for you to go and hear about JWST, talk about JWST, ask questions about JWST. And I think the last one is just, we're on track, and I think this is an amazing sight for me to see after all these years working on the mission, the mirror. And so get ready for JWST and use it. That's all I wish.
Okay.